It's Professor Dave. Let's solve some linear systems.
He knows a lot about all kinds of stuff. Professor Dave explains.
By now we have gotten pretty good at finding solutions to equations, whether they are linear, quadratic, or beyond. But what about when we have a system of two different linear equations? Can there be a solution to this set? Can there be a value or set of values that works for both equations? Usually there will be, so let's find out some different ways that we can get to this solution. First of all, since we are talking about lines, we can graph them. Say we have y equals x and y equals negative x plus 4. If we place both of these lines on the coordinate plane, we can see that they do indeed cross. If one line represents all of the pairs in x and y values that are solutions to one equation, and the other line represents all the pairs of x and y values that are solutions to the other equation, then it must necessarily be the case that the point where they cross must be a solution to both equations, because this point is on both lines. We can find this solution graphically if our graphs are very neat and tidy, or if we are using a graphing calculator, because as long as the graph is accurate, we can just observe that the lines cross at the point 2, 2, and therefore x equals 2 and y equals 2 represents the solution to this system of linear equations. Most of the time, two lines will cross precisely once, and there will therefore be one unique solution to the system. However, other situations include parallel lines which never cross, so there will be no solution to the system. And we could also have two different equations that describe precisely the same line, in which case there are infinitely many solutions, as every point on the line will be a solution for both equations. But as we said, we are typically concerned with situations where two lines cross once, and we want to be able to get that one solution. When graphing isn't so easy for one reason or another, there are other methods we can use to find the solution. The first technique we will look at is called substitution. Say we have these two equations, 2x plus y equals 4 and x plus 2y equals negative 1. What we could do is solve for one of these variables in terms of the other. For example, let's solve for y in the first equation. Subtracting 2x from both sides gives us y equals 4 minus 2x. Now what we can do is substitute this value of y for the y in the other equation. That means instead of y, we insert the quantity 4 minus 2x. Now we have a new equation with only x, which will make it possible to solve for x. We distribute the two to get 8 minus 4x, combine like terms, bring the 8 to the other side, and we get negative 3x equals negative 9, or x equals 3. That means 3 is the x-coordinate for the point where these lines cross. To get the y value, we just plug this x value into either of these equations. Using the top one, 2 times 3 is 6, and if 6 plus y equals 4, we can subtract 6 from both sides to get y equals negative 2. So x equals 3 and y equals negative 2, or the point 3, negative 2, is the unique solution to this system. Substitution isn't the only technique we can use. We can use another technique called elimination. Say we have another set of linear equations. Negative 3x plus 2y equals 11, and 5x minus 2y equals 5. Once again, we absolutely can use the substitution method, but it will sometimes be easier to go another route. We can combine these equations in such a way so as to get a new one where one of the variables has disappeared. To do this, in this particular case, we just add the equations together. This is valid because if a equals b and c equals d, then a plus c must equal b plus d. So we are just exploiting this logical truth to solve a problem. Negative 3x plus 5x gives us 2x. Then 2y plus negative 2y gives us 0. The y term goes away, and 11 plus 5 gives us 16. So dividing by 2, x equals 8. Then we can plug 8 into one of these, like the bottom one. We get 40 minus 2y equals 5, negative 2y equals negative 35, and y equals 35 halves. So this was a pretty fast way to solve this system. Of course, it won't always be as easy as just adding them together. Sometimes we will have to subtract. If both of the y terms were positive, we would subtract one from the other to get the y terms to go away. And we would then have to be careful with our arithmetic, making sure we get the right sign on all the values in the answer. Furthermore, we might have to multiply one or both of the equations by some constant to be able to do elimination. Say we have 11x plus 2y equals 13, and 7x minus 3y equals 9. The y values are pretty close, but we can't add them together as is and have them cancel. Instead, we have to realize that the least common multiple of 2 and 3 is 6. So we multiply the top equation by 3 and the bottom equation by 2. That gives us 33x plus 6y equals 39, and 14x minus 6y equals 18. Now we are ready to combine them, because positive 6y and negative 6y will indeed cancel each other out. That gives us 47x equals 57. We can then solve for x and plug back into one of the equations to get the y value. With lots of multiplying, the solutions can get messy, but that's just how they go sometimes. So in summary, we can see that we have 3 options available to solve for a system with 2 equations and 2 unknowns. We can either use substitution by solving for one variable in terms of the other and plugging that into the other equation. We can use elimination by manipulating one or both of the equations in order to combine them in some manner so as to get one variable to go away. Or we can just graph everything and see where the 2 lines cross. If they cross once, there is one solution. If they don't cross, there are no solutions. If they are the same line, there are infinitely many solutions. So why is this useful? Let's look at a real-world example. Say that Penelope and Artemis worked a total of 70 hours this week. However, Penelope worked 2 hours less than twice the number of hours that Artemis worked. How many hours did each of them work? While this example is relatively simple, and if we did some guessing and checking, we would eventually find the answer, that wouldn't be doing algebra. And if we learn the algebra, we can apply it to much more complicated systems where guess and check just isn't an option. First, let's write some equations. The 2 of them worked a total of 70 hours, so let's write P plus A equals 70. Then we know that Penelope worked 2 hours less than twice what Artemis did, so P must be equal to 2A minus 2. There's our 2 equations with 2 unknowns. How shall we solve? In this case, substitution seems pretty easy, as we've already solved for P in the bottom equation. Let's put 2a minus 2 in the place of p in the top equation. That gives us 2a minus 2 plus a, or 3a minus 2 on the left. We add 2 to both sides, divide by 3, and we get a equals 24. Then we can use either of these equations to find p. 2 times 24 is 48, minus 2 is 46. So Penelope and Artemis worked 24 and 46 hours this week. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.